Good morning and welcome to another webinar in the Industrial Heating Equipment Association series on sustainability and decarbonization. My name is Gary Berwick, member of the IHEA Board of Directors, and on behalf of the Trade Association, thank you all for joining us. We are excited to continue this series on such an important topic for everyone in our industry. Be sure to check out the rest of the IHEA sustainability webinars on the website. I'd like to announce that IHEA is launching its 2024 Industrial Heating Decarbonization Summit planned for this fall. The purpose of the summit is to forge a sustainable path to decarbonization for the industrial heating industry. We are finalizing dates and the location now, and will send the webinar attendees a save the date notice shortly. Information will also be posted on IHEA's website, IHEA.org. I hope all of you will plan to join us. Before we get started, I would like to remind everyone that all attendees are on mute. If you have any questions along the way, please type them in the questions panel. Each speaker will address questions at the end of the webinar. All attendees will receive a brief survey after the webinar. It will take just a few moments to reply. We appreciate your feedback as IHEA continues this critical initiative for the industrial heat processing industry. And one last announcement. This webinar is being recorded and will be available in the sustainability area of the IHEA website within the next few days. You will receive an email link once available. We have two presenters this morning. First, we will hear from John Carroll with Southern Company, one of the country's largest energy suppliers. John will give a broad overview of carbon capture and sequestration. John is a subject expert for Southern Company's Net Zero Technologies Group. John has been involved in the National Carbon Capture Center, a U.S. Department of Energy sponsored research facility managed and operated by Southern Company. His recent projects include front-end engineering design studies for retrofitting carbon capture for natural power generation, renewable hydrogen production, battery electric and fuel cell electric vehicles, and supporting technology testing at the National Carbon Capture Center. Our second presenter, Christian Toya, leads policy communications at Heirloom Carbon. Christian will highlight Heirloom Carbon's technology for direct air capture and storage. Christian leads policy communications at Heirloom. Before joining Heirloom, he served as the chief speechwriter and climate policy advisor to Fijian Prime Minister and the United Nations COP President Frank Bainimarama. Thank you for being here today, John and Christian. John, please take it away.
Thanks, Gary. That was a very kind introduction. I just wanted today to give some background on kind of carbon capture and the technologies that make up that space and kind of give you a level set on where things are today and where things could be going in the future. All right, so just to give you a quick outline, first, there's some terms that we all probably need to be on the same page for. We'll go over those in an overview. Then there are four main types of capture and separation technologies that I'll walk you through and kind of explain the pluses and minuses of each. And then we'll wrap up with kind of a current state of technology development. And hopefully we'll have time for a few questions at the end. So a lot of terms get thrown around in carbon capture, and they're not necessarily intuitive the first time you hear them. And so it's important that we kind of level set and all be reading from the same sheet of music, so to speak. So first, carbon reduction versus carbon removal. So carbon reduction is taking an existing point source of emissions. So maybe it's a big boiler, and you've got emissions coming out of that boiler, and you use a technology to then reduce the amount of emissions that actually leave that boiler and go to the atmosphere. That would be carbon reduction. Carbon removal is a technology that removes CO2 that's already in the atmosphere. And so reduction is focused at point sources, removal is focused on the atmosphere. That's kind of the first thing to level set, because it'd be really easy to think, hey, you're removing carbon from a gas stream. Why is that not carbon removal? It's just the way the terms have been laid out, but important to understand the differences. Then within carbon capture, there are really three main focus areas of ways that you can separate carbon from a gas stream. One would be what's called pre-combustion carbon capture. And there you take a hydrocarbon or a fuel and you basically break it down or crack it into hydrogen and CO2 before you ever combust it, so that you can separate the CO2 to where it won't be emitted at that point. Post-combustion carbon capture says, I'm not going to actually break my hydrocarbon up front. I'm going to go ahead and combust it or use it however I'm going to use it. And then I'm going to take the CO2 out of the combustion gases on the back end at that point. And then kind of a third offshoot there would be oxy-combustion. So that says, you know what? If I take the nitrogen out of air and I just have fuel and oxygen that I'm combusting together, I'll basically have a pure stream of CO2 and water on the back end, and those are pretty easy to separate. So I'll just do it that way. I'll use oxygen instead of air. And there's pluses and minuses to each of these. Different applications are going to make more sense. But most folks are focused on post-combustion CO2 capture right now because that is the easiest to retrofit to an existing process. There's not a lot of changes on the front end or the back end or inside the process itself. It's the easiest thing to then bolt on to the back end of the system. So CO2 capture is really about separating the CO2 from the stream that you're targeting. And that is the challenge, is how do you do that most effectively? There's some things that can impact how big of a challenge that is in different cases. So if you have a lower concentration CO2 stream, the penalty for separating it, whether that's heat or energy input of some other sort, is going to be higher for the amount of CO2 you get out at that point. Because of that, you want to maximize efficiency of these processes to minimize the energy penalty, and you want to reduce the equipment size to minimize the capital cost. All of these things add up to whatever it is you're going to pay to do CO2 capture, and so you can do that with, you want to do that with the least energy and the smallest equipment for the smallest cost. And then different applications may dictate different separation technologies. So the plant characteristics will determine integration. Some technologies use heat as part of the process, some don't. Depending on the availability of heat, depends on whether that process is a good fit. And then the CO2 end use could impact the requirements as well. Some technologies have an easier time producing a very pure stream of CO2. Others struggle to reach that same level of purity. And so depending on what you're going to use the CO2 for, whether that's maybe the beverage industry or sequestration, could impact what technologies you can choose at that point. And then, as I mentioned a minute ago, most current abatement applications are focused on post-combustion capture because we already have developed the processes we're using to make different things that help drive our world. And we don't necessarily want to reinvent those processes. We just want to decarbonize them. And so right now, post-combustion capture is one of the more straightforward ways to do that. So now digging into the technologies themselves, first, we'll look at absorption, which is carbon capture by solvent. So solvents are liquids that can take CO2 into the bulk phase of the liquid. So if you pass a gas stream through that liquid, the CO2 will bind with the liquid and the rest of the gases can leave at that point. So how that works is flue gas or a process gas enters typically the bottom of a big vertical column. And as the gas goes up, you have the solvent flowing down the column. And as those come in contact, like I said, CO2 binds to molecules in the liquid. And then you have what's called a rich solvent that leaves the bottom of that absorber. So it's rich in CO2, and it goes over to a separate process unit called a regenerator or a stripper, where the CO2 is stripped out of the liquid by applying heat to it. So the liquid can absorb CO2 at low temperatures, but then it releases it at higher temperatures. And after the heat is applied and the CO2 is driven back off, that solvent can then be recirculated back to the absorber in a big figure-8 loop, basically, at that point. So you're catching CO2 on one unit, releasing CO2 on the other. The benefits of these technologies are that you can really achieve very high capture rates, 95+% pretty easily. And you can produce a very pure CO2 product stream. Typically, there is a chemical reaction involved in removing the CO2 from the gas stream. And so it's very good at getting just CO2 and not getting other things like oxygen or nitrogen. And the component processes are well understood. We use absorption and stripping processes in the chemical and refining industries already for other molecules. And so we know how these work. We're just using them for a slightly different application at this point. Challenges for absorption technologies are this is really big equipment with really high capital cost. There's a significant energy penalty to heat the solvent and drive the CO2 back off. And you do have the potential for emitting some of the solvent. Typically, these are going to be volatile compounds, and so they can leave with that CO2 lean stream and be emitted to the atmosphere. And so you've got to make sure that you control for that as well. For absorbers, the key is to maximize the amount of contact that the liquid and the gas can have to really drive that high capture. You want to minimize the pressure drop to prevent high O&M costs, and then you've got to control the solvent conditions to avoid those emissions that I was talking about, those unintended emissions of the volatile compounds. The challenges to scale these up are the bigger this equipment gets, the harder it is to maintain a uniform liquid distribution within the column. And it gets harder and harder to minimize unintended losses at that point. But that's what research is focused on, is making sure that we understand the mechanisms and how to avoid those as well. And then on the regeneration side, really a big thing, and especially as you look at new industries to apply carbon capture to, is how can you maximize heat integration and minimize heat losses? So this is an energy intensive process and a thermal process at that. We want to take advantage of every bit of heat integration that we can within a plant, but eventually there's going to be a CapEx exceeding the OpEx benefits potentially at that point. So understanding the best ways to integrate that heat is important. You also want to minimize the potential for any undesired chemical reactions. While you have to heat these solvents to drive off CO2, when you heat them up, they can break down as well, and they can form degradation products, which could be, hazardous to personnel exposure, or it could just be an added cost that you're having to replace the solvent material at that point. And so understanding how to balance capital versus operating cost and maintain the conditions that will maximize efficiency are really important when you're looking at solvent-based absorption systems. Another set of technologies would be adsorption. So I've been emphasizing the B versus D there. So adsorption is carbon capture by solid. So instead of using a liquid, you have a solid where CO2 will bind with the surface of that material due to its physical properties or even its chemical properties embedded in that surface. So you flow a gas stream across this material, this adsorbent, and CO2 binds to the material as it goes through the system, and then everything that's not CO2 can leave on the other side. At some point then you have to flip that around, and you have to then again heat it to drive the CO2 product out, or you can also swing the pressure or some combination thereof. The benefits of using a solid instead of a liquid is you can eliminate water from the mixture, and you can decrease the energy penalty of driving that CO2 back off because you're not having to heat water. You can also produce a very pure CO2 product stream with much less potential for volatile emissions because you don't have a liquid that can be evaporated as easily. And just like solvents, we use sorbents for other purposes in industry already, and so we understand the component processes really well. Challenges for this remain that this is large equipment with high capital costs, and you've got to have a material that's durable and reliable. So if you have a liquid system and your material starts to break down, you can kind of have a bleed and fill system where you're making up solvent really easily. If you have a solid that's packed into some vessel, that's going to be pretty labor intensive to go and change out that material at that point. And so you want to avoid that both from a capital and a labor cost perspective from your process. And then how do I make this process intensified enough to where I minimize any downtime when the equipment's not either adsorbing or regenerating CO2 at that point? Because if it's just sitting there, it's just a cost that we're carrying at that point. So optimizing it, again, you want to maximize the contact area between the solid and the gas stream while minimizing pressure drop, because pressure drop means cost. at that point. And then you got to have effective heat transfer to make sure that you actually maintain the capacity of the material over time. Scaling them up is challenging because you've got to make sure the materials are durable. They're going to last long enough to make this process worthwhile. And again, you've got to make sure the equipment is running, not just sitting and carrying costs. On the regeneration side, you've got to have a really careful purge control typically on sorbent systems to maintain CO2 purity, because you want to then you'll be able to put it in a pipeline or sell it into the market at that point. And you've got to, again, have effective heat transfer so that you're not wasting heat as you're regenerating the CO2. We want as much heat as possible going into CO2 production and not into heat losses. Challenges, again, the same really on this for both the adsorption and the regeneration side. A third technology type would be membranes. So this is carbon capture across a barrier. So you may be familiar with membranes from some other separation techniques. Typically, water purification would be a good example. Reverse osmosis is something people think about. But this is going to be a semi-permeable material that will let CO2 cross the material, but will not let other things in a gas stream cross the material. So the gas is typically compressed, and then it goes into the membrane. CO2 crosses the material and comes out as a product, and everything that's not CO2 exits the other end as the emission gas at that point. Benefits for membranes: this is not something that requires heat. So if you had a facility where heat was challenged, you could use this instead. And so it's an electrification of carbon capture. It's typically smaller equipment with lower upfront capital costs because you're compressing that gas stream, and so the separation can occur in a smaller area. And you don't have a potential for new emissions because you didn't introduce anything new to the stream. The challenges for membranes are really about material durability and reliability. So if that material breaks down and starts letting things through that aren't CO2, then you don't have the product that you're looking for. Or if the material kind of plugs up, like any kind of filter can, think about even like a simple example like the air filter in your HVAC system at your home, you're going to end up having less throughput at that point, and that can also be a problem. It's difficult to achieve the same CO2 purity and capture rate that you can with solvents and sorbents, and I'll explain a little bit why on the next slide. And then the lower capital costs are going to be offset by higher O&M due to compression. So it's a little bit of, do you want to pay in capital or do you want to pay in O&M? Either way, you're really going to end up paying the piper. So membrane materials work by basically a differential concentration across the material. And so you can kind of look at it in this kind of illustration as the more CO2 there is in a stream, the more of it can cross a membrane barrier. And as you have less and less CO2 in your stream, you're going to have less and less flux across that membrane material. And so there's a couple of terms that describe this relationship of things crossing a membrane. They're permeance and selectivity. So permeance is a word that describes how much CO2 can cross the barrier, what the rate of transfer across the material is. Selectivity means how much CO2 versus, say, nitrogen in this case will cross the barrier. And so the unfortunate thing is you have an inverse relationship typically between permeance and selectivity. So the more CO2 you can let through, the higher rate, the more of other things you're going to end up letting through as well. Whereas if you want a very, very pure CO2 crossing it, you're going to have a much lower flux across the material. So optimizing those is really important. We also have to minimize pressure drop. I said that we're having to do compression on these typically. That's cost, that's energy you're having to put in to do compression. And then there typically are things that you can do to a process to make it more membrane amenable. So if you can adjust the process to maximize the inlet CO2 concentration, so the amount of CO2 going in, that will create better performance in the membrane material. But the challenges to scaling them up really are making a material that's durable in a variety of process conditions. And then you are going to kind of hit a linear cost curve with membranes because of modular construction. And so you don't get the same economies of scale as you scale these up. The final technology type that I'll talk about are cryogenics. So this is carbon capture by phase change. So CO2 is interesting in that it can change directly from a gas to a solid. And so that's typically what cryogenic technologies are doing. They are pressurizing and cooling a gas stream to the point where CO2 becomes a solid, like dry ice. That's what solid CO2 is. And so you put it through its paces of cooling, compression, and then some type of separation, and you can produce a CO2 product and a lean gas based on just the thermodynamic differences between the technologies. The benefits of this, again, because you're compressing the gas stream, the equipment's typically going to be smaller and less expensive. Because you're not adding anything to the stream, you don't have a potential for new emissions. And you can have a very pure CO2 product that can be collected as a liquid. You can create the solid and then melt that as into the liquid phase for transport, which has some benefits. The challenge is this may be difficult at large scales and large flow rates of CO2 because, frankly, you can only build compressors and heat exchangers so big. So there's going to kind of be a limit there. And your lower capital costs are, again, offset by higher O&M because not only are you doing compression, you're really doing some type of refrigeration at that point as well. So the interesting characteristics of CO2 is what makes this possible. So the triple point of CO2, meaning the point where it can basically, if you change the temperature or pressure just slightly, can go from gas to liquid or gas to solid or solid to liquid or solid to gas. That's actually at reasonably achievable conditions. CO2 will change phase much before, say, oxygen or nitrogen will. And so you can put it into the solid phase while leaving everything else in the gas phase. And solid gas separations are really effective. It's pretty straightforward. And then pumping liquid CO2. So if you froze it into the solid phase and then melted it into the liquid phase at that point, pumping a liquid CO2 is actually much more efficient than compressing CO2 as a gas. So CO2 that is going to be stored underground or sequestered underground needs to be in this supercritical fluid region. And so it's more effective to pump it as a liquid up into the supercritical region versus compressing it as a gas. It's going to be less of an energy penalty to do so. And so even though we used a lot of energy to cool that CO2 and pressurize it, then we save some energy on the back end. So just to kind of summarize the state of technologies, none of these have an inherent thermodynamic advantage over the other. Really, it all comes down to being pretty close to equal, all things considered. But they all have strengths and weaknesses. And so the specific application is going to help determine the right technology fit. If you're looking kind of left to right here, membranes and sorbents, they're on the left. Those are going to be economy of scale solutions. The bigger they are, the cheaper they're going to be on a cost per ton of CO2 basis. They're thermal solutions. They need heat typically to operate. And they are going to, they're already kind of well understood technologies. We do these other places. On the right, you've got membranes and cryogenics. These are electrifications of carbon capture. They are modular technologies, and so they're going to be manufactured, and then you're just going to stack units as you try to scale up at that point. And they're going to be higher O&M, lower capital. So depending on your situation, a different technology may make more sense than another in that scenario. But there's none that is a silver bullet solution for every single emission standard. And with that, I will take any questions.
We did have one question, John, about what level of temperatures are needed for absorption and adsorption.
Mm-hmm. So on absorption on the front end, you typically want to operate kind of in the lower 100s, I would say, maybe 110 F to 150 for absorption. Then in regeneration, you have to drive those temperatures up to maybe 240 to 270 F for most solvents. There are a few that can operate at higher temperatures than that, but that's kind of the difference you're looking at there. Basically an elevated ambient on the absorption side, and then kind of a low pressure steam temperature on the regeneration side. Adsorption is going to be similar in most cases. The temperatures can vary a little bit more because some people also use pressure swing, where they basically pull a vacuum on the adsorbent material, and that helps drive off CO2 as well. And so then they don't go to as high of temperatures.
We also had a question that I think Christian's going to answer about what are we going to do with all the captured CO2. So we'll see what Christian has an answer
I'll
for
just
that.
give a quick note on that. Is most of it's going to have to be stored somewhere, whether that's through enhanced oil recovery or just sequestration. But there are some utilization opportunities that are developing as well.
I'm looking to feed my soda stream off my water heater, not having to buy a little compressed CO2 bottle. So
hey, I mean, maybe that's the house of the future at that point.
All right. So next, Christian, please tell us about direct air capture.
Sure, I'd love to, Gary. Is my screen sharing or?
You should be the presenter now. Yep.
You can see my screen?
Not yet, no. You should be the presenter now if you want to just check it. There you go. Perfect.
Okay, all good, I assume. Okay, thanks so much, Gary. John, thanks for that lead in. And I appreciate you pointing out the distinction at the top around point source carbon capture and carbon removal. A lot of different terminologies here that can be a little confusing, so I'll just kind of reemphasize that again. Carbon removal is capturing carbon dioxide that's already present in the atmosphere, and direct air capture is one pathway within carbon removal. Sounds very similar to carbon capture, distinction being we're pulling CO2 that's already present in the atmosphere. Heirloom is one direct air capture company. I kind of want to start out at a high level today around why there's a need to do both, to do carbon capture where that's feasible, and why there's also a requirement to remove CO2 that's already present in the atmosphere. Go into a bit about the differences in these different pathways and the ways of, sorry, did I lose my screen here? Or?
Yes. There you go, it's back.
Okay. The different kind of pathways and how Heirloom's taking a swing at it. And then talk about the storage, where that CO2 it needs to be sequestered in order to kind of satisfy some industry definitions of permanence, et cetera. And then go into kind of what the scale up looks like for technologies like DAC, direct air capture. So here you're looking at the kind of scientific consensus around what pathways are going to limit catastrophic climate change, which is, the reason why we're here talking about this issue today. On the left, you'll see a column that assesses annual emissions by the gigaton. So this is billions of tons of carbon dioxide in the atmosphere. You can see the business as usual pathway there. And then you can see the second pathway here is decarbonization only. So this is, the emissions reduction stuff, of which carbon capture is a piece of as well. This is actually reducing the carbon intensity of everything we're doing across the economy. And as you can see here, that decarbonization only pathway still leaves us emitting, 10 to 16 billion tons of carbon dioxide every year from 2050 onwards. So the carbon removal, the justification for carbon removal, as you can see here, is what it gets us from decarbonization to a path that limits temperature rise to 1.5 degrees Celsius threshold. Now, I've personally been chasing that target from Suba Fiji to the Paris Agreement to now. It's essentially a threshold beyond which we're going to see some pretty serious impacts, and the justification here being if we're reducing emissions and then also removing emissions, so doing both concurrently, we have a chance at limiting the worst. So here you're looking at kind of all the different decisions that companies and countries need to make on their way to reducing their carbon intensity to net zero. As you can see here, carbon removal is what puts the net in net zero, because this is a complex economy. It's not as simple as just flipping a switch and decarbonizing everything and moving forward from there. We have to not only sorry, that's my wife. Reduce the emissions, we have to also then remove a segment of that. But we have to do that in a way that's not going to completely upend the operations of businesses and the economy. So on the right here, you said the low-hanging fruit, like solar, offshore wind, hydropower, biomass power, nuclear power. As you can see here, those are, in some instances, cost savings, in some instances, relatively affordable ways to start decarbonizing. Then you get into the slightly more expensive realm of electric vehicles, boiler electrification. These are going to cost a little more. Then you get into the carbon capture space. And then you get into a segment of the economy where there's just no affordable or feasible ways to get the actual carbon intensity to zero. These are the hard to abate emissions, the difficult to decarbonize sectors, and they're essential to the economy and they're not going anywhere. By 2050, we're expected to these emissions which we'll call residual emissions, are expected to be about 16 gigatons a year. These are industries like cement, iron and steel, plastic, agriculture, trucking, aviation. What a lot of these industries have in common is that they're some of the only few commodities we produce at multi-billion ton scale. And unfortunately, they're also some of the most difficult to bring down on the decarbonization pathways. Hence the need for direct air capture. So when you're able to actually pull that carbon dioxide out of the atmosphere, you can account for residual emissions in some of the most difficult to decarbonize sectors of the economy that are still going to be emitting by mid-century, by 2050. Direct air capture is one such option for removing carbon dioxide from the atmosphere. It's become a popular pathway. You've seen a rush of capital and interest from buyers and project financiers into DAC because it's got very clear measurability and verifiability. So you can point to exactly the amount of CO2 that you're capturing from the atmosphere and then going on to remove. You can do that on a very small land footprint. You can do it in a very additional way. So there's we've probably all read a bit about the controversy of these offset markets where you're flying on a plane and planting a tree and saying that that's accounting for your carbon emissions because you didn't cut the tree down. I think there's been a lot of justifiable controversy in those offset markets for that reason. When you're pulling CO2 out of the atmosphere, there's no question as to whether or not that's an additional service or you're actually accounting for that CO2 because it was going to be in the atmosphere until it was removed. And you have other pathways for carbon removal like carbon mineralization, where you're using a mineral that's naturally thirsty for carbon dioxide and you're spreading it out maybe on a farm or et cetera and letting it absorb CO2 from the atmosphere in a very passive way. Interesting pathway as well. The capture materials tend to be very inexpensive like lime or basalt, but you're using a lot of land to do that and it's unclear how much CO2 you're capturing. So there's some MRV is the terminology for that, measurement, reporting, and verification. Some concerns there. I won't get too commercial here, but Heirloom is a combination of direct air capture and carbon mineralization in that we're using a natural input of actually limestone to pull carbon dioxide from the air. Limestone, obviously, very cheap, very earth abundant. It's 4% of the Earth's crust. It's available almost anywhere in the world. It's an input for concrete, use it in chalk and toothpaste, very safe, well understood material. And it's composed of a molecule of carbon dioxide and calcium oxide. And when you separate limestone from carbon dioxide, you're left with calcium oxide. And if you were to take that, or it's known as lime in the construction industry, and if you were to take lime and just spread it out on the desk in front of you, it would slowly start to absorb CO2 from the air around it to reform into limestone, into its stable state of limestone. The problem is that would take years. These natural processes, they work very well at absorbing carbon, but they take a very long time, and we need to move that onto a human time scale if we're going to get serious about removing carbon dioxide from the atmosphere at scale. So Heirloom's process is we start with limestone, we put it into an electric kiln. Now, this kiln's electric. It's also designed to capture all of the CO2 that comes out of the reaction. So we put the limestone into the kiln, we heat it up, we separate a pure stream of CO2 from calcium oxide, and we take that calcium oxide and we put it on these trays, like a baking sheet that you'd bake cookies on. And we stack them in these very tall towers and expose them to the ambient air. And we treat that lime in such a way that it absorbs CO2 from the air and reforms this limestone in just 3 days And we take that limestone, we loop it back to the beginning of the process, we put it back into the kiln, we heat it up, we separate the lime, and we loop limestone over and over and over again to remove CO2 from the atmosphere at scale. And that's Heirloom's process. There's a lot of different direct air capture companies that are doing this in different ways. Actually, the sort of sorbents that John spoke about in his presentation as well are also kind of being used in the direct air capture space, where you're taking a big vacuum and you're cycling in, bringing in air and bonding it to the sorbent to capture the carbon dioxide, and then taking that, heating it, taking the carbon dioxide and storing it. But that leads me to the next part of this discussion, which is, where do you put this CO2 once you've captured it from the atmosphere? I'll start with what Heirloom's doing now, which is, in February of last year, we pioneered the storage of atmospheric CO2 into concrete. So you take the CO2 you captured from the atmosphere and you inject it into the reclaimed water that's used to make concrete. The benefit of that being that it mineralizes. So that goes from being a supercritical fluid to a mineral and forms as a part of concrete. And the benefit being it's a durable store for CO2 that, for our purposes and for the buyers who are purchasing our credits, we're keeping that CO2 out of the atmosphere. Even if you blew up a building made out of that concrete, that CO2 is a mineral. It's going to stay embedded amid the rubble for centuries. We're using concrete now because it's a durable store and it's immediately available, and very interesting repository for carbon moving forward. And there's going to still be a lot of concrete around for the rest of this century. By 2060, we'll be building a new New York City every day. But that said, even if you were to store all of the carbon dioxide that we'll need to be removing by 2050 into concrete, you'd only account for about 5% of that chart I showed you at the earlier part of the presentation. Because by mid-century, we're going to be needing to remove 5 to 16 gigatons of carbon dioxide from the atmosphere every year. The sheer volume of that is just very hard for even myself to get my head around. But if you're talking about the things that humans already do at multi-billion ton scale, concrete, steel, fossil fuels, carbon's going to need to be the fourth thing by 2050 that we're accounting for, moving, transporting, storing at the multi-billion ton scale. So the options for sequestration, therefore, they has to be permanent. We have to have some place we can store this CO2 where it's not going to re-enter the atmosphere. And it's going to need to have the volumes that are large enough to account for all this carbon. Now, miles underneath the surface, I mean, anybody who's worked in oil and gas understands pore spaces and the kind of volumes that are available for storage miles beneath the Earth's surface. The classification that the Environmental Protection Agency has for the CO2 sequestration, for permanent CO2 sequestration, is Class 6 wells. There are 5 online in the United States right now, several, I think 100 in the queue. States like Louisiana have been given primacy to actually establish these Class 6 wells for themselves. And in the process of CO2 sequestration, you're injecting carbon dioxide at a wellhead miles beneath the Earth's surface into these saline aquifers, generally with a capstone over the top of them. Very secure. This practice isn't new. It's been going on for about 40 years in the United States, mainly for the purposes, as John named, for enhanced oil recovery. Obviously, in this case, we'd also be needing to just sequester CO2 permanently, regardless of the need for EOR, simply as a new sort of economic model of just sequestering CO2. Heirloom is actually building a facility in Louisiana where we're going to be storing CO2 geologically, as it's called, in a Class 6 well. I think these sorts of projects actually have a lot of bipartisan interest and support, because they're going to create economic opportunity in areas that have traditionally been fossil fuel reliant. I think the logic being, any workforce that's developed the expertise to extract CO2 from underground is going to be pretty good at storing it underground as well. And they're going to have the workforces, they're going to have the geologic pore spaces and the infrastructure that's associated with transporting and storing CO2. The benefit also of direct air capture with regards to storing it in these Class 6 wells is that you can locate as near to the wellhead as humanly possible. You know, you're limiting your need to transport the CO2, which can be, you know, quite unwieldy, depending on where you're building in the United States. Deploying these, you know, these CO2 pipelines from all these different sources of emissions to a wellhead is a complex operation. With DEC, you can co-locate and basically do the capturing of the CO2 from the ambient air right at the place you'd like to inject it. Cover this a bit. I mentioned the Heirlooms building in Louisiana. So the Uncle Sam is playing the role of angel investor a bit with the direct air capture space in the United States, because they want to see the U.S. kind of take the lead on the jobs that come out of this this industry moving forward. The Department of Energy's, through the bipartisan infrastructure law, has provided matched funding for these direct air capture hubs across the states. Heirloom was lucky enough to be notified of selection to build a megaton facility. So it's a 1 million ton capture capacity, removal capacity facility in Southwest Louisiana. That accesses up to $600 million in matched funding. I can't say that hand over heart we've got that $600 million. We're still in the negotiation phase with the DOE. Moving forward on that, there's another hub being built in Texas. Again, these aren't quite first of their kind facilities. There are commercial facilities. Heirloom's operating a commercial facility in the United States at the moment, but these are going to be the first and largest megaton facilities for direct air capture in the world. Still, megaton facility, 1 million ton annual capture capacity, drop in the bucket relative to where we need to be within the next few decades, but a very important start for showing how these commercial facilities work at very large scale. I want to talk a bit about the buyer ecosystem, why there's a business case for direct air capture, how this purchasing and procurement of these credits work. So in direct air capture space, your business model is that you're selling a credit that constitutes a net ton of carbon dioxide that's been removed from the atmosphere. That's a net ton. So you're considering all of the embodied emissions associated with actually building the facilities themselves, transporting the CO2, powering the facilities to run. Once you've accounted for all those emissions and you've removed those emissions, you can sell a net ton of carbon dioxide, so a truly additional ton of carbon removed from the atmosphere. These purchase agreements are generally very long term. We signed an agreement with Microsoft in September of last year to remove 315,000 metric tons of carbon dioxide from the atmosphere over a 10+ year period. Now, the facilities that are going to service that purchase requirement have not been built yet. This is a model that really accelerated the deployment of renewables, where you're locking in prices and volumes over a long term, so that the supplier, Heirloom in this case, can go out and actually build the facilities that produce the credits that go to this buyer. So when you're able to do that, obviously you de-risk on the demand side. You're able to attract a lower cost of capital and actually get these facilities built. And we are operating at a commercial scale already. I mentioned earlier, we pioneered that storage of atmospheric CO2 in concrete. We're doing that at scale now in California's Central Valley at a facility in Tracy, California, that has a capture capacity of about 1,000 tons per year. Very modest, very small start, but we're showing how this technology works at scale. As you can see here, those are the towers of trays that are exposing calcium oxide to the atmosphere, where they're absorbing CO2, reforming into limestone. And we're using that as our the CO2 we capture from that is going into concrete in partnership with a company called Carbon Cure, and it's going in support of Bay Area infrastructure projects. This is obviously very Heirloom specific. It's just showing the rate at which we've kind of deployed this technology. In 2020 was PhD research. July 21, we were capturing about a kilogram of limestone in a petri dish, of carbon, in a petri dish using limestone. And we opened this facility in November of last year. Just want to emphasize again, we're proud of this pace of execution, but in order to get to the gigaton scale, this technology is going to need to really, really ramp up at this pace, if not faster, between now and mid-century. But that gives you kind of a sense of the logic behind the business model for direct air capture, what buyers are looking for in terms of the credits that are being developed, not only that these are being additionally removed from the atmosphere, but that the CO2 is being permanently, durably stored away That's the kind of model that's in the voluntary market for now, scaling this up. I think it's important to note that buyers who are looking at direct air capture at the moment, it's a very energy intensive, difficult thing to do, capture carbon from the atmosphere. It's very dilute in the atmosphere, as John mentioned. At a point source, you're getting a very high capture rate because you're right at the source of emissions. Carbon that's already in the atmosphere is much more dilute, so there's energy associated with actually pulling that CO2 out of the air. But as this scales, and as you're able to do it at a larger and larger scale, you're going to see a cost down in terms of the price of removal per ton. And this industry is coalescing around about $300 per ton by 2030 and $100 per ton by 2050. Not cheap, but when you're looking at all the different decisions that need to be made in order to reduce the carbon intensity across the economy, when you're getting into steel, aviation, trucking, some of these really, really difficult to decarbonize sectors, the price of those decarbonization solutions is off the charts. So when this is available at those lower price points, it's able to account for all those very difficult, very expensive, if possible at all, to decarbonize sectors of the economy. And that's generally the space that DAC's operating in. I'll leave you with that. There's a list of our buyers to date. This is kind of the pathway to achieving 8 million ton scale and then eventually gigaton scale. This is a rendering of the megaton hub that we're building in Lake Charles, Louisiana, Project Cypress. Very excited about that next stage of this project and continuing to bring this technology to bear and into the market. Thanks very much.
Yeah, thank you, Christian. Very, very interesting presentation. I wonder, like I was thinking to myself, like as a consumer of electricity in the Detroit area, I could pay for green power. And so I wonder if there's a market for people. I think of like our favorite Taylor Swift, who she's paying for carbon credits for her private plane. Go get her as your spokesperson and you can offset all her carbon use. There's a marketing idea for you.
Yeah, actually, there's a lot of interest in that. She's offsetting her flights right now with kind of the traditional offsets, which are, as I mentioned, have some controversy in those markets around whether or not those are actually accounting for the carbon associated with what they're offsetting. But yeah, a lot of aviation is obviously one of those very difficult to decarbonize sectors, regardless of the Swifties and their interests. You're going to see some evolution in SAF and sustainable aviation fuel that can reduce the carbon intensity of that sector a bit. But generally, if we're most likely going to be flying more today than we are, more in 2050 than we are today. There's going to be more emissions associated with air travel, and SAF can only get you so far down the kind of the emissions curve. So DAC's going to play a role there as well, for sure.
I invite people to type in questions that the gentleman asked at the first presentation about, what are we going to do with this carbon? And I think that was answered. We're going to put it underground.
I've taken my screen off, right?
Yeah.
Yes.
No, it's good information. It's like you said, there's no silver bullet here. There's going to be a lot of solutions, a lot of partial solutions. That's what I'm seeing.
Yeah, exactly. It's basically costing out what every decision is going to cost in order to get to net zero. And then direct air capture carbon removal is going to start playing a role when each marginal abatement cost starts going into the stratosphere at the tail end of these graphs, which is, as I mentioned, those heavy industries, very difficult to decarbonize sectors. We've got to find a way to account for them. And John, interested to hear your perspective as well on this. There are some areas where you can fit carbon capture into a system, but there are other emissions that are just, it's quite unwieldy to account for every ton of CO2 that's going out there via pure carbon capture. So both are going to have a very major role to play.
Yeah, you're going to have both, and making sure you apply them in the right places is really important. Like aviation, I think, is maybe the single hardest emission to abate, because despite what you might have seen about electric planes or hydrogen planes. Those are pretty far away. The energy density of a liquid fuel is really hard to match. And so we're probably going to be reliant on jet fuel for a very long time. And so DAC is going to, I think that's one of the places DAC is going to play in the long term for sure, is accounting for aviation emissions. We also need carbon in our economy for a lot of the products that we're pretty reliant on. And so as we move away from fossil fuels slowly, we're going to lose some of the carbon sources we've been relying on, and making sure we kind of close the carbon balance to make the products that we wear, to create the fertilizers for the food we eat. And we should kind of hope that population continues to increase and demand continues to increase. So we've got to have really a good focus on getting carbon where we need it and preventing releasing it where we don't as well. Like it's kind of a multifaceted issue.
We have a question here from someone asking how much energy is needed, like how many kilowatts is used to remove a kilogram of CO2 or carbon. Any feel for that number?
I don't have a kilowatt number off the top of my head, but a lot of point source capture applications are going to be in the neighborhood of 2.5 to 3 gigajoules per ton of CO2 removed. For direct air capture technologies, that can be a little higher because you're trying to regenerate from a less concentrated source, but it varies. And the regeneration energy is only one part of the story. You've got energies otherwise to move things around. So in general, the more concentrated the CO2 source, the less energy is required to capture it and then prepare it for storage. And the less concentrated, the higher the costs go at that point.
I believe at the kind of slightly more scaled up version that we're operating at today, we're looking at 1,500 kilowatt per hours per ton of CO2 removed. I don't know. I don't have it to the kilogram, but per ton, 1,500 kilowatt hours.
Yeah, that's fine.
But it is energy intensive.
Yeah,
I just
another
want to echo that point again, and it's important as well that if as you're removing CO2 from the air, and the way these markets are going to start valuing kind of the service of carbon removal, they're going to count the emissions associated with removing the CO2 from the air. So direct air capture is also, it's very important that it's sourcing renewable energy in order to do this service. We're powering our first Tracy facility 100% renewables because it decreases the carbon associated with removing the CO2. And as we scale up, we're going to be a hugely catalytic customer of renewable energy as well. We've made it a point to make sure that we're procuring additional renewable energy. So we're actually paying into the creation of new renewable energy projects. And energy's the chief cost driver for DAC for the reasons of diluteness I mentioned earlier.
Yeah, someone asked about the longevity of your site, like your Tracy site, which is sort of your pilot plant. Do you guys have a feel for how long that'll be able to be in operation? Your kiln will probably need to be
Yeah, well, the kiln will need to be repurposed depending on how high we crank the temperatures. But at a very, in order to account for those embodied emissions I talked about earlier, you need to complete a life cycle analysis of the facility. For Tracy, you're looking at about a decade, which we're considering the service it provides and the emissions associated with it. Actually, we anticipate to run it for longer than that as an R&D site. It's our first site. It's near our HQ. We're in California, and it's we're going to try out new kind of towers, new kinds of types of limestone, new kind of cycle times, etc. As an R&D site moving forward. But generally, as we build larger facilities, we want these to last for decades in these areas and actually continue to scale up from the original site. If we find an area with the kind of right mix of workforce, sequestration, social license, and we actually really like humidity for our technology as well. So when we set up in a facility, in a hub, so to speak, we expect to be there for decades.
And some people have put up DAC sites with a good source of geothermal power to try to be green with the power.
Right. That's right. There's one other commercial facility. There's two commercial DAC facilities in the world. One is our facility in Tracy. The other is in Iceland. It's run by a company called Climeworks, and they are using geothermal energy to power that site and sequester the CO2 into a basalt reserve. Now, I talked about Class 6 wells as a great sequestration site. Basalt is also a really great material to inject CO2 into because it mineralizes very quickly when you inject CO2 into basalt, and that's what's happening in Iceland right now. There's actually a lot of basalt in the Pacific Northwest, which is an interesting area for DAC deployments moving forward. And actually some recent activity in the geothermal space in the United States of exploring kind of areas where that has a lot of capacity, which will be a signal for any kind of carbon removal tech to site near, including DAC.
I think that's it for all the questions. I thank you two gentlemen. I mean, I'm in awe of your knowledge. I think this is an important issue, and we need more knowledgeable people in the world. Believe me, we need that. So I thank you for your time. I thank you for your efforts in this. It's going to be really important moving forward.
Thanks for the chance to speak. And if anybody has any questions, feel free to reach out. You can find me if you look.
Yep.
Yeah, so Gary, thanks for the opportunity to chat. And John, I really enjoyed your presentation.
Same.
To set things out. Thanks for that.
So to the attendees, thank you for attending this webinar. Remember to visit the IHEA website, ihea.org, and click on the Sustainability tab on the menu bar for more information on sustainability and decarbonization. Please watch for a link to take a survey and take a few moments to share your feedback. Have a great day. Thank you for joining us.